Swayam Prabha. Digital India. Educated India.
Okay, so now the point is that I will teach you today a topic called the magnetic properties of the inorganic metal complexes, suppose. Okay, so the concept is actually magnetism, and it is a bit of physics and chemistry, so it's interface. So we have to be really very have a different kind of mind. This is an interface, so a different kind of mind to take the concept. If you take it like chemist, what will happen, you will be lost. Okay, so here major things are the organization, arrangement, their component, and there is a bit of mathematics. Okay, so you take them like you go back to class 12 standard or something, where you have all kind of subjects and you are trying to get a concept. Okay, and there a little all will come and you build a concept and you apply to the next. Okay, nothing to memorize here. Okay, so suppose you are, each of you are having a spin center. Spin means you have unpaired electron, it will be one or more than one. Okay, and how they will interact with each other, and if they don't interact with each other, and when they interact, in what are the different ways they interact. Okay, you have to mind and what will lead. Okay, so if these two of you start becoming friend, and how you are, or you start becoming enemy here, how you behave, or you start sometime enemy or sometime friend, how they behave, or then I put three of you similar way, permutation combination, four of you, and this part, and then sometimes this part to this part, each part descend. Okay, they are having some meaning. So what will happen, you will lead to the different situations, and each situation is a kind of you can call it a kind of ensemble, and you have a microstate, and those will be having some property. So every state you will behave, that state will have a corresponding energy, and corresponding energy, it has a magnetization, and that we can measure. Okay, so all of your pocket and devices, chips, whatever you are using every moment, it is storing data, it is something going to magnetic chips. Okay, where spins are stored in the two domain and in the boundary. So up and down spin and the boundary, and in the boundary you are actually storing. So if you look at, you have the tiles between the where you have the separations between them, that is the area where you are actually storing the your energy, your information. So information are stored either as up spin or down spin. So what is up spin means? So if you apply magnetic field like this is your magnetic field, and your actually this is anti-clockwise, it is rotating the electrons, and your spin will be like will be upward. Okay, in the clockwise with respect to the upward magnetic field applied, it will be downward spin. So I first give you a concept, when you have a free electron in the sky, in the space, there is nobody interacting, it is spinning, but it has a like it has different way it is oriented, so it is random. Okay, so it will be no problem, but moment you apply magnetic field, this is your magnetic field B0, what will happen, the spins are going to take free electron. It's like somebody you have learned the EPR or like or the what do you call it, NMR, and those things you have studied, so it can be like this. Okay, so if you do like that, so what we call this kind of things, the anti-clockwise rotation or clockwise rotation, instead of like this we call them up spin and down spin. These are vectors. So vectors, if I write a vector, I write with a magnitude and direction. So a vector will have a magnitude and direction. So if you have a one spin, you can have a spin vector, and its magnitude is actually one electronic spin, and it has a direction. Okay. Now since it has direction, because it is spinning with respect to applied magnetic field and is different orientation, and these are the quantity which keep varying from complex to complex, and when you make bimetallic, trimetallic, and multi-center clusters. Okay, because those spins are interacting through with each other through something, either through space or through the bridges or through some bonds. Okay, so now you are going to slowly learn into complicated concepts where the spins are going to be a problem for you. Okay, so take it easy. Spins are like human, and if you treat the society, how each of you behave, how cluster of people are behaving every day, every places, as well as every place, what you see them that the spins also will behave. Okay, so the past example I give you, two of you are very good friend. Okay, so I put one spin here, and I spin the s equal to half, and then I put the another spin here, s equal to half. Okay. So now these are the thing you can consider the copper 2 plus octahedral ion, copper 2 plus octahedral ion, and they are not interacting, they are long separated. So you have come from the different colleges, you don't know each other, and you just sitting, don't know each other. Okay. So if I measure what's your like as a spin, what I will see them, I will try to get its what I need to know. What I need to know that how much magnetic momentum. So what you calculate? You have calculated magnetic moment equal to root over n into n plus 2, right? Number one. Another formula you might have studied, you have magnetic susceptibility multiplied by temperature, that product will be called 2.83 into root over chi t, right? This is new formula for you, all of you. Okay, so now I am suddenly bringing chi t. What is chi and what is t? So chi, okay, so now if you have a sample, so now I have a, this is a my sample vial, and it is filled with a sample all, okay. This is also sample vial, and this much actually sample is filled, fine. So now when I am putting magnetic field B0, and B0 is passing like this. Now what is B0? It is an invisible line of forces, it will pass like this, you know, right? So now it is going like this, and if it is paramagnetic, they will be trying to attract some of them inside it, and then some of them will be, most of them will be repel, I mean going outside. Similar case for this one, three of them are going inside suppose, and most of them are going outside. Okay. Similarly, because identical ions like that. If it is a empty space, okay, what will happen? Whatever will come, maybe two of them are going and rest all are going outside. Okay. If you fill it with a magnetic sample, which is actually much more magnetic, called ferromagnetic, okay, what will happen if you again same field you are passing, and all maybe all four lines are passing except one line. Okay. So in if you see, find a situation here, if you make the magnetism measurement, you have a machine, okay. That machine you have to put suppose 15 milligram sample you have in the physics department, and you pack it and wrap it in a diamagnetic sample container and put inside the machine, and they will center the sample, and they will apply the magnetic field, and sample will be fluctuating there. So they have a kind of in a electric magnetic field as an electric field, both are there, and then they are this fluctuating. So you know that if a magnet like something magnetic moment, it's a tiny magnet, they fluctuate it, they will be also inducing some current, right? And they have a secondary coil where they will measure the fluctuation of the flux and corresponding ring current, and then they can estimate your magnetization. Very simple. Okay. So our part as a chemist is not need to know those part, you just try to know how this will behave. So now in this case, when the field will go maximum will pull inside, so this will become magnetization will become highest among these four conditions. Okay. Here will be both are same, and here will be the what do you call it, medium. Another case is there where you fill this same space with the same amount of diamagnetic sample. So this is kind of paramagnetic, this is paramagnetic, this is ferromagnetic, okay, and this is empty, okay. Now and this is diamagnetic sample, diamagnetic, fine. So if you now moment over here you this one, what will happen? They do not like the field because they are having electrons which are paired with each other, and they have diamagnetic effect. They do not like to attract, they rather like to repel. So what will happen? Maybe one will go through them, and all rest 5 lines will be passing out. Okay. So in this case you see that more the number of lines passing through this space, we get more magnetization actually. So we get a material which is called diamagnetic. So for our body is maximum made of diamagnetic material. So we are, if I put inside the machine and try to measure in a big magnetic like a machine, and our majorly magnetic, this will be going outside, and we have some amount of paramagnetic ions and all, they also try to attack, but we are majorly made of diametric stuff. Okay. First, so now if you measure the its magnetization, so what is chi? Chi is equivalent to, it is a proportional to, this is by m by h. So what is m? It is the magnetization, the way you are calculating this kind of things, equivalent, and you are dividing by the field. So you, what is the field? We apply in Gauss or Oersted or Tesla, whatever. So field is nothing but, you have seen magnet, right? So its magnet has some kind of field, it has north pole and south pole. So north pole to south pole, the lines will start and come like this, right? And inside like this, right? And in the middle, and you have, they compensate each other, you have no nothing. But in the two top poles, you have the maximum, the lines will be coming, and then they will go coming like this, and you have also done some practicals, right? I hope with the pins and this magnet, and then you make drawings, and that is your magnetic field, and that is what you are applying here. Okay, and moment you take different kind of materials, and we are trying to see that, you say that, so why I should have play with the magnetic in the house, the other why I should play put it through the magnetic field here with the sample, because we are, as a chemist or physicist or material chemist, our job is to synthesize materials which will be good for our technological purposes or daily life. For example, you are really actually using, so the magnets you are using, they are having kind of platinum cobalt alloy and they are kind of nanoparticles you are using, okay, and they have they are kind of ferromagnet, and then you are using them, and you are using the your all what your pictures of your friends or parents or whatever, or any text, anything or you are saving, all are stored, your display is shown like word or something impression, but the information is stored as a unit data, either upspin or downspin and between the domain. So we have a two domains, and they are like, you people are two domains actually here, and data can be stored this side or that side in the border. Okay. Now, so now now why this you need to know, okay. So if you have to need to know, because nowadays this magnetization, people are trying to get as much as possible, and also they can control its upward or downward spin, and then they can maximize your data storage capacity. So if you have seen 10 years ago your your mobile, what was the capacity of the mobile data storage? 1 GB, 10 GB, something like that, right? 20 GB. So do you nowadays buy any mobile less than 60 GB? No, right? So at least it has gone by 3 times to 5 times the per person data storage capacity of their pocket device, right? Even somebody selling some bada or somebody riding auto, they also will have the this much minimum, right? So now what is the point? Point is that we are having more pictures, more videos, we have to store more. So if you want to store more, I have to put a bigger space in my mobile where I can store the data, or you kind of find a technology where in the same space you can store more data. So what you like to have? More data, yeah, that is what you have to do. So now being a chemist, you can have the laboratory where you have the chemicals, you can play around and mix X, Y, Z differently, okay, and you know how they are making them, and then take them and then put into the machine and then let it measure. Now based on the measurement, you want to see that whether I have made the material which can be storing the data, the one which I am already using, okay. So now if I can only produce a material which is even 10 times more storage capacity, you imagine same those people I have explained, now they can have instead of 60 GB in their pocket, in the same space they can have 600 GB, okay, fine. Now imagine I made a material which is 100 times or 1000 times or 10,000 times like that. So now in this way what you will do, you can one day take very tiny space and store all your data. So now you are buying, after a hard drive is filled, you are paying another 5,000 rupees, another 1 TB or 2 TB that you are buying, but you imagine 1 TB becomes 10,000 TB. So once you buy it in your lifetime, you may not need any more hard drive to buy. So that really smart. You play with some chemicals in the lab and you bring something, you put in your device, and that can work for you for whole life. Okay, and the problem is solved. Okay, so those kind of researches are going on. Another one is that you are processing data, signals and all, right. Now try to imagine you have heard called quantum computing. So what is quantum computing? So quantum computing means that I am here, I have 10 lanes, okay, and every lane can lead to the something, and I am trying to find one auto driver in which I have lost my purse. And now there are 10 lanes. I can take any auto, every auto will go to the sum of the one of the lanes. So I have to 10 times go to find where is he. This is normal like computational chemistry. Now another called quantum computing. It is at a time it will search in all the 10 lanes at a time. Do you understand the meaning? So instead of looking one after one and one by one at a time, where parallelly 10 lanes you search at a time. So done. So quantum computing, what does? A calculation which takes nearly 10,000 years can be done in 200 seconds. So in just nearly 3 minutes you compute everything what can be computed in 10,000 years. So that is the power of the quantum computing. Okay, and they need mathematical algorithm to code to be written, and then you can do it. So for that, they also have use magnet, and the magnetic field they need, which is close to 0, sub Kelvin. They are in millikelvin, so near 0. Okay, so maybe 0.017 or 0.0017 this is the Kelvin, so near 0. So that means you have to freeze that kind of magnet close to a temperature which is nearly 0, right? So now try to see how much your parents are paying for the bill for your AC in your house, and how much you are paying. This each AC per month cost minimum 8 to 10,000. One of this unit here you are sitting, and it is just cooling few degree. If it is 30 degree, it will go nearly 20 degree. You are just cooling 10 degree. Now imagine you are cooling. So you have seen liquid nitrogen, right? Vaporizing and all. It's like a smoke, and you go to like a helium temperature which is 4.2 Kelvin, even cooler, and going close to 0. It's really hardest job. So you have to spend lot of human power, technologies, manpower, and all the things costing you to go to the 0 Kelvin or close to 0 Kelvin, and then you are going to compute. So now point is that you can go get such kind of material which are very advanced in magnetic material, and they could remain magnet and can do the same job at room temperature. So problem is solved. Even they can be doing little high temperature because our global warming is rising. So we need those magnets to work at the higher temperature than they are working today. That is the job of the scientist all over the world, to find materials which will be making your life better and better. Okay. So now if you want to know about how the material behaves, how to control them, how to tune their synthesis, their properties, you have to know the bit of physics and chemical ways to make them. Okay. So now today what I am covering, the how to make their physical property now. Okay. So this is the importance of the field. Okay. Also can be done with some magnetic materials, they can very high spin. So what you can do, you can let the spin be upward with the applied magnetic field, and then you switch off the magnetic from outside, and then let them randomize. So when you apply the magnetic field, their order everybody upward. Now moment you switch off the magnetic field, they will get the heat, and they will try to randomize their spin, right, this way, that way. So that time they will take the heat from the outside and they will give you cooling. So that we call it magnetic refrigeration. So what you are doing, you are asking to get more randomized in terms of entropy and then take the heat from the outside and you are cooling. Okay. So those are the ways, in different ways these magnetic materials you can use it, use. Okay. There are organic chemists who are thinking organic chemistry, people are using or magnetic nanoparticles which have huge surface areas and some functional defects here and there. Active side where they do the catalysis, they are non-soluble, they are heterogeneous magnetic materials, they are nanoparticles, they are very magnetic. So moment you put in the solution and put your reaction component, all everything, you start stirring, suppose 10 hours it takes. You stir it, reaction done, and you want to separate it. What you will do? Put the one magnet bottom of it or side of it, all will come, then decant it, magnets are outside, your catalyst is coming out and the solution comes out, you process, and it is in just flash wash with this one, next cycle you can use it. So you can get recyclable non-magnetic nanoparticles or magnetic molecules which can do your job also. So they are mostly nanoparticles, insoluble. Okay, people are using it. So in these different ways, magnets you can use it, okay, everywhere. So when you are going for MRI scan, also they are dealing with our brain and this oxygenated brain, non-oxygenated brain. Oxygenated brain is more magnetic, and non-oxygenated more magnetic. After oxygenation is less magnetic. Then they are measuring your many things. Okay, so different way they call magnetic imaging. Okay, so in medicinal field, in the daily life, everywhere we are actually using magnet. Without magnet, nothing. If Earth is not having the magnetic field, we also have a problem. What is you have seen now? When you have called solar wind coming. Solar wind, you have seen coming, right? So what is solar wind? The every day you are doing this to Suryapanam. Surya looks from very far, very bright and hot and all. But if you more go to the close to them, it is a devastating case. What is devastating case? Is not only hot. It's not only hot. It is really very much magnetic on the surface. They have keep on producing magnetic flux and very high flux, you cannot imagine, and they are conflicting each other, and sometimes the fluxes are coming, then they are produced in the core. It takes 10 to 15 years or 1000 years, something like that, maybe 10 to 15 years, the one flux that come and to the surface, and then sometimes they conflict each other and some of the mass will be, materials will be ejected. So those are actually neutrons, okay, and then when they come, they will be what do you call it, protons, and then protons are not stable much, it will decay into neutrons and electrons like that, and then they are going to every direction, all, and we are in one of the direction, and when it comes a lot to our direction, then we said, oh my god, it's going to be solar wind. Sometimes there is an article, right, and when they passes, what will you have, it's like they are coming like this, and when it comes on you, it's like on wind, okay, but these are not normal wind, they are filled of high energy original particles. This particle physics, that particles, they are made either free electrons, they are neutrons, like that, okay. And now when they pass through your high energy things through your air on your around the earth or through the earth, what will do, they will try to ionize the gases and also blow away some of the gas molecules. So around the earth our gas molecules are weakly attracted and they are somehow staying, okay. So somebody is coming like a big demon bigger than earth, does for some times, and we will be losing, actually we are losing some amount of oxygen and water molecules like that from through the space, okay. If you count and over the million years, we are losing actually. So you wait for some million or billion years, Earth's atmosphere will become thinner and thinner and it will go and it will vanish. So now how we can retain this gas which we breathe and we take and we live in, it's like water for the fish, for us it's like water. And what is happening, these when they are coming through you, and then this gas molecule will be ionized, they will be lost, and that's how some billion years ago the Mars lost its magnetic field because it doesn't have magnetic core, this molten core, and molten core, the lavas they are flowing, and that is producing the magnetic field. Okay, and that magnetic field is weak, but that is important for us, for our sustainability on the planet. Mars lost it, it had everything like Earth, it has lost its air, atmosphere is lost. Our atmosphere is protected by the Earth's magnetic field. When this kind of solar wind is coming, it is producing the field and it is repelling those particles which also have a magnetic, and they are repelled and going passing through, and some amount are entering through the polar region. You have solar, that you have the aurora. You have seen that in the polar region, the aurora, right? Norways and all. And those auroras, because of the solar wind, those are the particles are entering and ionizing the gases, and they look like they're colorful. Different gas are ionized, there are different colors they can produce. Germans used to call the sky is in fire. Some people have used to fight like that, and it is the reason. And if you see the Jupiter, the biggest planet in this solar system, it has big ring like this kind of aurora, and which you can see from the telescope from the Earth. Okay, and because it has much more magnetic field, and effect is much more. Okay, so and that's how we are trying to, through the magnetic field, weak magnetic field we are having here, it is also protecting our atmosphere for billion of years. If molten this core is gone, we will not have the flow of these lavas inside. They are ionic and they are producing the magnetic field, and this magnetic field is like a kind like football every side, so like a symmetrical way, and protecting us from there. So everywhere we have magnet. Okay. So now let's go to the original concept. So these are the features of magnetic field, magnets and all. We can use it. Now let's go to the tiny things. Now we have defined that if we have taken B0 like apply field. So I have a magnet, I can switch on the sky here, it has circuit and it will produce make a magnetic field, and this magnetic field will be passing through your different cases, and I can measure and I can get this is the values. Okay, magnetic momentum. Now point is that what we have inside the every magnetic material, they have magnetic energy state. Okay, so whatever you talk in terms of the physics, it has to be something with the energy state. Okay, so now they have energy state, and every energy state they can be magnetic or diamagnetic. So if you have diamagnetic energy state, when you apply magnetic field, their energy will be little bit repelled and go up, and you have the magnetic, you have the what do you call it, the magnetic energy states, they will be slightly be stabilized and they will be down. Okay, and then you get something called total E. Okay, these are all magnetic energy levels. Okay, and then you have the whole all the energy overall all. So it is the summation of in 0 to infinity, and you have like this is a in here 0, I put it here. So now what does it mean? That I can have a E0, okay, then I can have a E1, like E2, like that, E and infinity. Okay, you have studied. So these, each of you, when you are applying the magnetic field, they are affected, and each of them, they can have different effect on the magnetic field, and then their overall effect will come as your magnetization. So the first derivative of the energy, this change in the energy and with respect to the magnetic field, is actually chi. So what is the chi? Chi is the magnetic, you can, if you take per mole, means Avogadro number of molecules, if you take okay, then per mole you get this chi all magnetic susceptibility. Okay, now this is nothing but del m by del h. Okay, so okay, and what is the m? M is the actually energies, this derivative. So this is actually second derivative overall chi. So change in energy with respect to applied field, you produce magnetization, and magnetization change per field, it will be kind of a chi. Okay, so if you have a, so suppose you have studied for copper 2 plus 1.73 is the Bohr magneton, right? Is the, what do you call it? Bohr magneton is the magnetic moment for the copper 2 plus 1 mole. Okay. Now, if you same material you can just convert it to here. If you put this one here 1.73 into 2.83 into root over chi t, if you do so chi t will be 1.73 divided by 2.83 and you have to square it because there is a root. Okay. So this is going here and you square it. So if you do that it will be coming around 0.375, okay, centimeter cube. So into unit is this one, centimeter cube Kelvin per mole. Okay. So chi is a unit, is like a volume. Okay. And since the temperature is there, so is a chi is the volume per mole, how much volume it will take per mole, and since T is coming, so this K has come, is a temperature, absolute Kelvin is coming. Okay. So per mole how much volume it will occupy this flux, it is actually the one which you call it chi, and it's if you multiply by T it is called, this is a chi T and we call it chi T product. Okay. This is the unit. Okay. Remember this, very easy. So now how to calculate this one also in this way. So now there is another one, you can take it chi t equal to this one, to third formula gives, I don't know, I will only 4 formulas total, 2 are done. Now second one is that n beta square g square by 3k into s plus 1. Okay. So this one you are knowing mu and I have converted to them into chi t, and then chi t also can be calculated from the spin values. So instead of going from there we can also directly calculate from here. Okay. How? So this is the one, is Avogadro number, beta you know the gas constant and all, right, and g is the gyrometric ratio, and k is the, this is the Boltzmann constant. Okay, kb, and this is the spin, each spin. So if I have this one, so they are all constant, sorry this is not cube, this is square. So n beta square g square by 3k s into s plus 1. Now if you put, these are the constant values, they all, these are the one coming to be 1 by 8, okay, kind of 0.125. So this is actually basically 0.125, okay. And then you have g square, g generally for copper 2 plus nearly 2 square, then if you put, if for one spin that is half, then half plus 1. If you calculate how much you get, can you calculate? Just calculate that one. 0.125 into 2 square, that means 4 divided by half, and then half plus 1. So you have got this value, right? 0.735, right? So we calculate, so if you do it, it will be coming 125 multiplied by 4, then here by 2, then you are getting 3 by 2 here. So these two you cancel, then you multiply this one, it will come 0.375. So this is the chi t for copper 2 plus ion, and it is centimeter cube Kelvin per mole. Okay. So we are writing mole inverse. Fine. So now you know for the copper 2 plus ion, and now if you have 2 of the copper 2 plus ions are there and they do not talk, the first case I have come, you see you have to just sum them up, or 2 times you will multiply by 2, that's all, right. So when you do not know each other, so they are called magnetically isolated. Okay. So now if I have 2 copper ions and they are not talking to each other, and they are linked whatever they are there, or they are very far, and they will produce 0.375 plus 0.375, and this is the magnetic, this is a chi-T value. Okay. So now if you can know how to calculate this much, is a big deal actually for MSc student, because then you can start building up your concept. Now if you say, so you have, it will become 0.75, right? 0.75 centimeter cube Kelvin per mole. Okay. Case number 1, very simple. So now I ask you, you have studied the structure of copper acetate. So we have started with copper ion, and we did so much to say something, only 40 minutes, and now you see that now I have to talk about copper acetate, a molecule, a textbook example of different things. So copper acetate having a monomeric structure or dimeric structure or polymeric structure? What's the answer? Copper acetate structure, you know, simple copper acetate. Can you each of you draw copper acetate structure? Copper acetate, yes. Copper acetate 2H2. So now if you have copper acetate, we write like this: copper acetate O2 CH3 something like that, 2 times dot H2O. Okay, this is the formula we write generally. Okay, and what is the structure? Basically copper acetate doesn't stay like this, it's not monomeric, it's actually dimeric. So basically it is copper 2 times acetate CH3, this is 4 times and 2H2. Okay. So now if you have this this is a dimeric structure. Now how are they? Do you know the structure? Can you draw? When you go for PhD interviews, they will ask you what is the structure of copper acetate and what is the magnetic momentum. Okay. So now let's draw copper acetate's the structure. Okay. So if you do not know how to draw a structure, at least you know that you have 2 copper, right? So what you do, you draw them like this. Okay. So 1 copper on the top here, and at the bottom here. Okay. Once you have drawn, at least you know 2 copper ions are there. So now you try to think that you have 2 water molecules for 2 copper, right? So put 1 water molecule here, okay, and water molecule here. Fine. They are not lattice water, they are coordinated water. So writing this formula actually basically wrong. Something is coordinated, you cannot write like this. You should actually write like this with the third bracket. That's the law of the Alfred Werner coordination chemistry formula. Okay, so the things already you know, for abbreviation is fine, but actually this should be written like that. So something is coordinated, you cannot write with a dot something. It basically should be right within the third bracket. And which is not coordinated, just secondary somewhere flying and saying the lattice molecule, this should be written after here dot. Okay. Now, moment you know that, now you only need to have 4 acetate. Okay. So now how you can draw that? You first take, don't become intelligent in the first case, become not intelligent actually. So you put it 2 acetate here like this. Okay, 2 acetate like this. Okay, and this is the acetate molecule I am drawing. Okay, fine. Similarly you draw it here. Now at least nobody can blame you that you are just guessing it, you don't need to know anything actually. Okay, but it is not then time, I mean they are not connected. So why I should write the formula like this then? I should just write like this. But so that means these acetates are not, 2 are not each time only bonded to 1 at a time. So what is happening? This is the 1, so it is bonding here. Okay, here, and this is the 1, it is bonding here. Similar case is here, and this is bonding here, and this bonding here. My structure came. So you can, if you do not remember anything, just write up and below or sidewise 2 acetate and each acetate will have one copper will have one water. You put it vertically or sidewise, whatever the way you want, and then draw per share, per copper, you will have two acetate. You draw them shielding fashion, okay, and then you know that they are dimeric, that means the ligand needs to bridge them. So we call it bridging ligand, okay. So now this copper acetate is behaving like this. So this one, in the middle one, it is the inter connected. So it comes like that. So instead of having copper rings like that, it is like this. Each copper acids are like this. What will happen? The coppers are like this, okay, and other two are like this. So they are clipping them. So if you take one acetate, there is two coppers are like here, one oxygen here, one oxygen here, and copper is here, copper is here. So two like this and two like this, okay. So this is your actually copper acetate structure. Now what to do this copper acetate today with my lecture today? Yes, now come here. I have given you example. Two spins are interacting and they are the two spin, two copper centers, and each of them are having one unpaired electron, and these electrons are now here and here. So they are all 2 plus. So you have 2 plus here and 2 plus here, and they have is equal to half here and is equal to half here. Now they are spin and they are not very far. They are distance nearly 2.7 angstrom or something like that. Okay. So they are below 3 angstrom, quite close, and they are spin. Now if you calculate, from your formula, from your perception, until I taught this much, it's supposed to come. If you take this one 2 times of this, it will come around 3.46. Okay. If you take equivalent, will be coming here this in IT. So if you measure, what you get, less, more, or the one that you get? That's my question to you. Less, less. Yes. So there are 3 possibilities. One, this value, the unchanged. Another one, more. Another one, less. So if you come with 3 possibilities, then you draw them. What are those? So I have a spin here and I have a spin here, and they don't know each other. Okay, they are blind with respect to each other. They do not see each other. They do not know each other. Okay, first case is called magnetically isolated. Okay, magnetically isolated. Fine. Number 1. Number 2, these 2 spins are there, but they arrange with respect to each other antiferromagnetic fashion, antiferromagnetic. So this is called antiferromagnetic arrangement. Okay. In this case, you see this is a vector upward spin. It has a momentum, okay, and it has a kite contribution of this way and that way. So if they are completely arranged in this way, and then you get no magnetic momentum. So what you have in hydrogen molecule, okay, in H2 molecule, this is the 2 spins, electrons are here, and one spin is up, another is down all the time. Okay. So when they are there, if your hydrogen molecule is diamagnetic, similarly in copper acetate, if they are like this, it should give a S equal to 0 overall. Okay, so S equal to 0, how they are coming? Plus half and minus half, because of this arrangement. Now third possibility, okay, you bring it here, both are upward spin. Okay, so if you do it here, this will become 1 overall, half plus half. Okay, so these are 3 possibilities. Now if you have this possibility, the 0 possibility, this one we have calculated, this is going to be this value. Okay, but they are not talking. If you put this possibility, if you put here S equal to 0, and whatever are there, everything becomes 0. So if you put copper acetate in the magnetic machine, whatever field you apply, it will give diamagnetic. It will not be giving any magnetic momentum. Okay. Now if you go to this possibility, it will give magnetic momentum. You calculate this value, put S equal to 1. If you put this value, can you put 1? So how much it will come here? till this much is same 1 into this. So if you do this 1, how much will come? 1 point something, not 0 point. So 1.128 equal multiplied by 8, it will come nearly 1.01. Okay, so that means if you keep two spin parallel to each other, instead of getting this much, I will get little bit more. Okay. So, but you people said that it is little bit less than what I should expect. So that means there is something to do with its interaction with each other, right? Because it is lower value is coming means it is in antiphonically coupled. Sure, right? Indication. So as a scientist, what we do? First, whether we have a coronavirus, we do not know. Then we start getting catching cold or sneezing or having fever, we don't know. Then symptoms are developing. So our symptoms are that the values are less. That means they are antiphonically coupled. So this is not the case. So the top one is not the case, and this is also not the case, and here this is the case here, and then if it is antiphonically coupled, this should have been completely 0, but it is not 0 also. So what does it mean? That if you take Avogadro number of copper acetate molecule, diacetate this one, Avogadro number of this, not this. If you take this, you have to take 2 times Avogadro number. This is your formula. This is Avogadro number of this dimer. Now if you take, they start arranging themselves in different ways. One is they are not interacting or they are randomized. Second one, they are interacting. One is upspin and is downspin. Third type of molecule where both are upward. Okay. Now I am cooling down the sample and I start measuring the same magnetic momentum what I get. Okay. So we take a break, you think of for 5-10 minutes in your and you see that if you cool down, what will happen to this sample, and every temperature I cool from room temperature, I take a value, then I cool down to 5 degree. Okay. So I it's now around 25 in this room. Now go to 20 degrees centigrade, 15 degrees centigrade, 10 degrees centigrade, then 5 degrees centigrade, 0, then -5, -10, like that, keep on going towards 0. And you think whether the magnetic momentum will remain same or there will change. So we will call it temperature dependent magnetic susceptibility. So earlier we have done just susceptibility, now we are measuring the same quantity but at different temperature. And you say, sir, why you need to cool it? Because that's what I told, that many materials are behaving at the low temperature. If you can improve the material, you can add room temperature, you can work, and then you actually use them in room temperature. So our job is to finally control the temperature of the property. Okay, where it will be the best way of finding something, and then we can control them and tune them. Okay.
SwayamPrabha, Digital India, Educated India.